I'm Paul Davies, slightly checkered history. I spent 29 years with Thales, but about 6 months ago I moved to Network Rail. I'm also visiting fellow at this university and visiting professor at two others. This is one of my own personal research interests, and also it's linked to the research programs of three of your NDIs here who are sponsored by Thales. They know who they are. And as Patrick said, I'm a past president of INCOSI UK, so I've been involved with quite a lot of stuff there. What I'm going to talk about today is quantification of the value of systems engineering. What is the correlation between system engineering activities and value added to businesses? A lot of what I'm going to talk about is based on two very strong research outputs. The first one is a study by the National Defense Industries Association in the US, which is a not-for-profit brokering organization from, as it says, mostly defense companies in the United States. Plus, they contracted an organization called the Software Engineering Institute, which is an arm of Carnegie Mellon University. And some of what I'm going to talk about, the copyright is owned by Carnegie Mellon. Okay, we have got rights to reproduce here as long as it's not for commercial gain. Now, that's I need to say that. Second thing to say is the second research study is the work of a guy called Eric Honor, who is a self-employed consultant, again in the USA, but he was convinced to undertake this research by the University of South Australia in Adelaide, the initiation of Professor Stephen Cook there. They and some US companies funded him to do his research. He owns the copyright on that, but he's given me kind permission to use it. And I managed to interview the lead authors of both studies. I managed to get 2 hours with Joe Elm, who's the lead author of the NDIA study at an INCOSI conference in Philadelphia last year. And I got another 2 hours with Eric Honor himself at the conference on complex systems and design and management in Paris last December. So I did most of this work while I was still working for Thales and just finished it as I was leaving. What I am not doing, I am not speaking on behalf of Network Rail for reasons that I will explain as I go through. Okay, so treat this as if I'm presenting on behalf of Bristol University. So I do have to publish this, and this needs to be in the video and on your website. Is a formal acknowledgement notice of Carnegie Mellon's release of copyright. Right. Why is this presentation important? 14 years ago now, Sarah Sheard, another seminal author in the systems engineering world, and Chris Miller, who I think worked for a software productivity consortium at the time, published a paper, The Shangri-La of Return on Investment. And in it, the abstract actually says, this paper will show that 1, there are no hard numbers, 2, there will be no hard numbers in the foreseeable future, 3, if there were hard numbers, there wouldn't be a way to apply them to your situation, and 4, even if you did have them, no one would believe you. However, time has moved on. There has been some background work by Professor Philip McPherson, who was at City University at that time, and did a lot of work with companies like Shell to try and do quantification of systems engineering value. And then the NDIA studies and Eric Honor's work. So I'll talk a bit about Philip McPherson's model and Jack Ring's model of value. decompose what we mean by systems engineering for the purposes of those two studies, what activities are included and what frameworks have they got and what's the provenance of them. Then talk about each of the studies and to do some back-of-the-envelope return on investment calculations as my own personal deductions from the outcome, particularly of the NDIA study. As a result of that, you could deduce, in principle, which system engineering activities show the greatest return on investment. But it's not as simple as that. Organisations don't adopt best practice in a logical manner. Well, or rather they do adopt them in a logical manner, but it's not the logical manner that you would hope for in terms of maximising return on investment. And I'll talk a little bit about why. The studies both show measurements of competence. Okay, so the correlation of beneficial business outcome with organisational competence. So I'll talk a little bit about how we measure that. And I'll do some conclusions. So first thing, the value life cycle. I'm hoping most people in the room will have seen this. It was proposed by Jack Ring some while back. We start with a problem discerned in the community situation at the top of the cycle. We have a problem discerned with it. We do some work to understand the nature of that problem, and then we propose a solution effect. Okay? We envision it, we specify it, we come up with an intervention strategy for trying to solve that problem. Then we go through what we would normally consider to be the systems engineering V cycle, which is very much the bottom half of that egg shape. So we envision a proposed system solution, we architect it, design it, do the components. Then we work back up the other side, validation, verification, validation. We activate it in the environment, and we measure some operational results, and we manage to measure the real effect of the system solution rather than the intended effect. The context itself adapts. See James Martin's 7 Samurai paper for a really good description of that. And we can put some quantification of the value of the system, but then we go round again because the insertion of the solution system into the community situation solves some problems, but the context has morphed. There'll be more problems to solve again. Moving on from there, Philip McPherson's model takes that and looks at it in a slightly different way. He postulates that we've got what he calls SCP, a phase of the life cycle of a solution system, which is about the system creation and the project to put it into its operational environment, if you like. So the boundary of that is delivery into a customer or operational environment. And then we have what he calls SOX, system operation and experience. So we realize value of that system in its operational context by operating it, supporting it, and iterating through upgrade loops, which may themselves require new system creation projects, and then retire it. But there is additional value created outside of that box by intellectual capital and systems praxis. Okay? There is an organization or an extended enterprise that is responsible for bringing that system into being. And value is created inside that organization, which is not usually delivered with the system. The experience is gained by the individuals and the teams and the organization from actually conducting that project and solving that problem. That intellectual capital can be valued because what it implies is that the next time that team performs an intervention for a similar problem context with a similar system solution, they will do it more efficiently, and therefore they will capitalise on that value acquired by doing the project. And in principle, Philip says you can get a total value of systems engineering because you have a matrix of feeds of intellectual capital, praxis, potential value from the original system architecture, the value added by the project, and then successive cycles of operation and upgrade. And there may even be some residual value when you dispose of it. And you've got different stakeholders who perceive values in different ways. Core stakeholders from within the organisation creating the system, and stakeholders involved in the life cycle itself and the operation and disposal of the system. Now, I'm going to go on to talk about these two research studies, and a key point to notice is that both of them focus on the system creation and project part of the whole life cycle. Okay? They don't explicitly consider the value created within the organisation through intellectual capital and acquisition of competence on the left-hand side. And because the surveys and studies focused on the prime contract organisations who were delivering the projects, they don't explicitly consider the value to the operational stakeholders of the system entered into its operational use. So it doesn't consider the right-hand side either. However, the assessments of value created through the projects must obviously be coloured by what has happened over on the right-hand side here. And the whole point of this exercise in terms of calculating the return on investment in improved systems engineering practice is putting a value on that. Okay? So, and Philip calls that instrumental value, the value of delivering something, extrinsic value, the value of that system in its intended operational environment, and intrinsic value, the value to the organisation that put it in place. Okay, so let's start to talk about a bit about metrics and value measurement within systems engineering. Some things we know. This presentation really speaks to those who are responsible for putting systems engineering into practice in their organisations. Richard. So some things that people who are responsible for that really ought to know if they don't know already. The first one, how much will the project cost? This is taken from, Eric helped me track down the original source. There's a chap called Werner Gruhl, way back in 1985, working for NASA. And he looked at correlation between project overspend and overrun versus the amount of that effort, of the originally budgeted effort that was spent before before given the go-ahead for the full project. I think they call it decision point A, where you've done feasibility studies and preliminary cost analyses. And I'll just skip ahead to the next slide, but I wasn't sure whether I had copyright release for this, but Eric assures me we have, that it's in the public domain. So we're looking at, if you only spend 1% of your total estimated budget before that contract award point, you're going to overspend by anything up to 200%. Whereas if you spend more than 10% of if you spend 10% of your budget pre-contract or prime contract award, you're limiting your overspend to about 25-30%. Werner Gruhl drew a different regression line through those data points That is Eric's, I'm pretty sure. When I squinted at it visually, I thought you probably reached the law of diminishing returns at about 8%. And what that 8% represents, I clarified this with Eric, is not just systems engineering. It is all sorts of project definition work to do with the overall integrated engineering. Okay, so it includes a certain amount of project management activities in a similar way to I believe, to the NDIA study. Okay, and that 8% does not include later systems engineering activities such as integration, verification, validation, testing. Okay, so the second one. How does systems engineering cost or overall project cost scale with project size and complexity? There are many ways of doing this. The software community have looked at function points, and the Scrum people have developed different metrics. Or in systems terms, you could just do a basic count of requirements given a certain level of granularity in how you specify your requirements. Uninformed accountants may think that cost goes up linearly with scale, all right? Most engineers, if they think about it, would postulate that it goes up with the square of the number of requirements just by looking at the number of interfaces between different subsystems and therefore the requirement subsets. I had a summer student some time past who found a study by Fred Brooks, and I have lost the reference and I can no longer find it, so if anybody could find it for me, I'd be very grateful, who showed a large cross-industry software project study showing that it goes up with a cube. And I got my student to plot number of requirements versus spend for a smattering of real projects, and it kind of fitted, apart from one here, which is way off the scale, and we knew that that one was in dire trouble anyway. So its costs were out of control. And the other thing to say about that is that not just your cost, but the size of your error bars goes up with at least the square, maybe the cube. So what does that do in terms of your bidding risk margin, your likelihood of containing your costs within what you're bidding for the job? And I think there's insufficient appreciation of that in the project management and finance communities. Okay, third one to notice, and this is from an excellent book by Larry Putnam and Ware Myers. Again, it's quite old, it's over 15 years old, and they showed a characteristic shape of project effort per unit time against elapsed time on a project. I've seen a theoretical derivation of this, which I won't bore you with, but if you take 3-point estimates for a large number of activities that form a work breakdown structure, and then do a Monte Carlo simulation of chaining those estimates together, you get this Rayleigh curve. And it shows some interesting things. There's a limit to how fast you can bring people onto a project, for example, so this curve approximation is not perfect. You always see spikes in it, and those spikes tend to correlate with major review points in projects. So there's my system requirements review, there's my system design review, there is my first set of subsystem integrations, here's my first go at the acceptance test, and here's the actual field trials and major in-service transitions. So it always works. And what's more, your exposure to risk, if you do your risk management properly, also looks that kind of shape. And if you add your risk exposure to your actual distribution of effort over the lifetime of a big project, the two added together make it a different Rayleigh curve with different parameters. They did quite a lot of work on parameterizing in terms of team expertise, size of project, I forget, there were a number of other dependencies, so that you could use this to do forward prediction of parametric estimation. And one of the things they did show is that you cannot arbitrarily compress a project timescale by throwing more people at it. And they managed, theoretically and empirically, to correlate with the observed behaviour that if you add more effort to a late project, it makes it later. Recommended read. Okay, right, and the fourth one is, and this is where we get to the real crux of spending systems engineering effort on early project timescale activities. Published through NCOSI, a guy called Bill Haskins, who worked, I think he's retired now, for Boeing, on the cost of fixing errors versus the phase at which you discover them. If it costs you $1 to fix, if you discover an error in your decomposition at the requirements phase, it's going to cost you 250 times as much, typically, if you discover after you deliver it and it's in operation. Because you've got to recall it, you've got to go right back to the beginning and do your redesign of flow down, you've got to follow it up with all of the documentation, the testing, operator's manual, logistics support, the whole 9 yards. And that costs a lot of money. So, by inspection on that, spending an extra $5 on taking time to get the requirements right and your design right early on in the project is obviously going to pay dividends come the back end. So why can't we do formal quantification of that? And the reason is that nobody's going to fund a randomised controlled trial for a £1 billion job. So you have to work out what you can do, and there are also too many environmental variables. All right, I've listed some of them here, but the most important one that we might want to concentrate on is organisational competence level, because by taking a large enough cross-industry sample and working out a way of trying to renormalise for that, we can at least deduce some correlations, even if we can't deduce cause and effect. And I will come back to that. Oh, and please don't get me started, or get Patrick started for that matter, on the effect of politics on project outcomes. Right. So, this and the next 8 slides are copyrighted by Carnegie Mellon, and we're talking about the NDIA survey, National Defence Industry Survey. I've added a note at the bottom, again, saying it was about the point up to delivery of the projects, not beyond and in service. Value to an in-service operation may be higher, it may not. I can't work that one out in my head. But what they observed is a very strong correlation of high business performance with high organisational systems engineering capability. I'll explain a bit more about that as I go along. That correlation is noticeably higher if the project is deemed to be more complex, more difficult, more of a challenge. And there are, breaking down overall systems engineering capability into some of the constituent practices, the strongest correlation observed is with systems engineering planning, requirements development and management, verification, and product architecture. And I'll say a bit more about some of those as we go through. I apologise for the spelling of program, but I'm reproducing some of these slides and content verbatim from the American. Okay, so Joe's presentation started with this, and the arguments on the right-hand side, I've seen every single one of those in finance director, program executives, arguments against doing systems engineering. and without quantified answers on value, you're in a weak position arguing against them, which is the point of doing this work. But I'd be surprised if anybody hadn't seen those in the organisations in which they work, even if you're students trying to get funding for doing it. Do stop me on the way through and challenge if you violently disagree with anything.
I've seen that argument against computational fluid dynamic analysis.
Yeah.
So it's anything new. I think, come back to it later, I always struggle separating systems engineering from the rest of engineering.
I'm not going to go into that one, given my current employer. Okay, how did they do it? What they took CMMI and IPDIPI, or Integrated Process and Product Development. There's a standard on that. They took a total number of 25 process areas and 479 work products, and they filtered it down for maximum relationship, led by a panel of experts who you can't expect to have been objective about it, but we'll let that pass, and got it down through a size constraint filter so that they could reasonably expect the respondents to reply to the survey, because they weren't going to assess their projects against the 470 odd work products. They would have just got a nil return from the survey. And they focused on those things, 13 process areas and down to 71 work products in the bottom right hand corner. And they did get a reasonable response rate. The other thing is that they assessed total program performance, not just costs, not just schedule, but adding an element of technical performance, in particular the level of requirement satisfaction at the point of delivery, as well as meeting milestones and compliance with budget. And they also asked for an assessment of program challenge, how difficult it was, and the level of prior experience, whether the team concerned had previously done projects of this type before. Okay, and they didn't try to do it too quantitatively. They used a 4-point Likert scale, and they did not use absolute values. They used relative rankings amongst the responses from an individual organisation, and they looked at the correlation between the systems engineering effectiveness and the program performance. Okay, so that anybody who claimed that everything was scored 4 in their organisation on either program or systems engineering effectiveness, that would have been relatively discounted to eliminate bias. They did ask for a random cross-section of projects, a mix of successes, indeterminate and failures. They didn't get it, and I'll come back to that in a little bit. And they carved up the systems engineering activities that they wanted assessed for effectiveness by the respondents from the organisations concerned into those 11 activities. So program planning, which sounds like a project management activity, and to a certain extent it is, but it's about planning of engineering activities on the program, particularly integrated engineering, not single discipline engineering or single subsystem engineering. And then down through what we would recognise as systems engineering activities, and then finishing with program monitoring and control, again, of the engineering activities. So there is a genuine mix of systems engineering and engineering management activities in there. The study, the responses were fully anonymised, and there were 2 studies, one in 2008 and one in 2012, and they went back and de-anonymised the 2008 studies to improve the to challenge some of the data and improve the practice of responses to the survey prior to the 2012 study. The key slide in its entirety, the bottom line. This is about program performance versus total systems engineering. Okay, so the sum total of all of those systems engineering activities in terms of effectiveness within the respondent organisations for given projects. And it's in a 3x3 matrix. Basically, of all the responses, they took top third, middle third, bottom third in terms of successful business outcome, top third, middle third, bottom third in terms of systems engineering effectiveness in terms of the ranking orders, and then plotted what fell into which category. And there are some interesting conclusions that Joe has drawn there. So for lower systems engineering capabilities, so this is this left-hand third, only 15% deliver high business performance. Okay? So and likewise, for higher systems engineering capability, you only achieve inferior program performance 20% of the time. Okay? And this measure of statistical significance, gamma of 0.49, claims to be very strong. A researcher at St Andrews, who I got to look at this, says actually looking at that statistical measure, it's not that strong, but it is noticeable. And my total assessment of this, putting the systems A team on the job more than trebles your chance of the top third project success compared to putting the C team on the job. Given that, the median value of the projects in this survey were $488 million. So your A team might only be as good as the median C team in this study, which is a sobering thought. Okay? The effect of program challenge. So we've got on the left-hand side, low program challenge, what that effect is. And over here, the really difficult ones, the really large, complex projects. And what that is telling us is that for low program challenge, improving the system C team to B team standard doesn't give you that much. However, the A team doubles your chance of success. And on the right-hand side, if you put the system C team on a job with a high degree of difficulty, you stand a 92% chance of not getting a good outcome. That's a big number. Okay? And you get a 3x3 like that for each systems engineering practice. For example, requirements here. Now this is an interesting one. I picked this one because I've seen this in practice. If you if you do more and nominally better requirements practice, so improving your practice from C team standard to B team standard, your effectiveness can actually go down because they're doing more requirement stuff, but they might not be doing it effectively. They might not be focusing on the right things. Your chance of failure does go down, but your actual return on investment up here isn't that great. But once you get to A team standard, it makes a hell of a difference. And you've got similar 3x3s here for high program challenge and low program challenge. And for low program challenge, if you do more requirements definition and analysis for stuff that really wasn't that difficult in the first place, your best performing projects don't get any better. In fact, you get fewer of that top third of business outcomes. Does that make sense? Right, okay. Well, okay, going back to how they did the study, they looked at how Okay, it was partly subjectively marked, but the responding organisations, on a scale of 1 to 4, marked the team doing that job overall and against each of those 11 practices. Okay? And then you just take average values and divide the whole set of responses into top third, middle third, bottom third. Yeah? Took me a while to get it as well. All right, and correlations. So we're talking about the correlation gamma factors between each practice and business benefit. So the so point 1 there just says that's the sum total of all systems engineering practices, how good you are at the full range. And that's nice because that tells us that the whole is greater than the sum of the parts. Yeah. Number 2, project planning scores the next highest. That is particularly interesting because in the 2008 study, it wasn't. It was way down. Joe Elm tactfully suggests that because this has got a bigger and better statistical sample. I have a private theory that it's because they allowed a mix of responses to this from project managers and systems engineers. But I can't prove that, so yeah, I can't take that any further. Likewise, configuration management and monitor and control scored really quite low in the first study. In fact, the correlation with monitor and control was in fact negative, which tended to show that the better project controllers you put on a job, the worse the business outcome. But it's important to separate correlation with cause and effect. It's the programs that are already beyond saving where you put more project control effort on. 4 is interesting. Validation and product integration score quite low, but hold on to that thought for organisational evolution reasons that I'll come back to. Number 5, prior experience. There's good correlation overall. If a team's done this kind of job before, it has a positive effect on business outcome. The interesting thing was that for high challenge projects, the answer is worse. Okay, so for high challenge projects, having a team with prior experience doesn't help you as much as it does for low challenge projects.
What do you need experience in what?
In the application of systems engineering to the domain.
It's not the practice, it's the student solutions.
That's one interpretation, certainly, is that the fact that high challenge projects always encounter problems that you haven't seen before. Okay, so the prior experience doesn't help you as much as you thought it might. Mike, yeah.
Reading across solutions that you worked on previously into a new problem context, so an experienced team brings those preconceived notions about how to solve the last problem into the current problem.
Yes.
Situation.
Yeah.
Is also contributing to that.
It is contributing to that. I think that's very much the case, and it tends to work for low challenge projects, okay, which you could put under the banner of precedented projects. Okay. What else have I got to say? Oh yes, 6 and 7. Where did 6 go? Oh yes, 6 is about project challenge. That means the higher the project challenge, the worse it correlates with business benefit. And 7 is interesting. Trade studies and architecture scored lower in this study than it did in the 2008 study. In the 2008 study, they were the biggest single correlating factors with project success, which is interesting. Right, that's just that, which you can have as a takeaway once you get it online. So, what does that mean in practice? What does that tell us about return on investment and anything you can quantify about value? So, what the finance director will say, okay, well, how much is it going to cost me to implement appropriate systems engineering? How much is it likely to cost if we don't do it? And what's the marginal benefit? Now, in some organisations, it doesn't work like that, in that you are not allowed to use cost savings as a justification for spend. Yeah, or cost avoidance, I should say. MOD is one of them, and to some extent, Network Rail is another one, to some extent. And should we just invest in the competencies with the highest payoff? Right. So I did some broad brush assumptions about ROI. If the distribution of SE capability within our own organisation conforms to those 3x3s from Joe's study, percentage-wise, if we can use representative gross margin figures for high, medium and low business outcomes, and if we can estimate the amount of our turnover that we spend on development or engineering in total, and then the amount of the percentage of that effort that we spend on systems engineering, and if we make the massive assumption that improving your systems engineering capability would lead to a concordant improvement in performance, then I've got two example business models. I've got Company Alpha, which is really quite profitable. The top third of its business projects score 25% gross margin, but even the bottom third get 10% gross margin. They've got a reasonable production volume so that they can amortize their development cost, so they're only actually spending 10% of their business costs on engineering or development engineering, and they're only doing 12% of that on systems engineering, which is what Werner Gruhl's study and Eric Honor's study say is about optimum. And we've got Company Omega, which has moved into the prime contracting arena and is struggling. So it's got a reasonable top third project's gross margin, but its bottom third is actually losing a bit of money. This is not unrepresentative. And because they've moved into the prime contracting arena, aren't manufacturing very much, 25% of their business cost is development, and 20% of that is systems engineering. So, what does that mean? It means that if you plug those into the overall systems engineering 3x3s from the NDIA study, you get that for Company Alpha and you get that for Company Omega. Right. So what can we deduce from that? You deduce that your expected margin goes up from the C team to the B team to the A team for Company Alpha quite linearly, and it's not that dependent on the project complexity, which is interesting. Conversely, Company Omega, which is concentrating on high challenge projects, the relative performance as you move from C team to B team to A team is really quite big and makes a huge difference to gross margin. That's only part one. So what can we do about that? I've got two strategies here. Strategy A is hire and fire. Fire the C team, get rid of them. But you've got to recruit some people to replace them and recruit higher performing replacements at your envisaged B team or A team standard, but you've got to pay them 25% more. All right, I've seen companies do that. Or strategy B is grow your own. take 10% of your B team out on a scrolling basis each year and put them through an intensive training course, master's degree or whatever.
So there's a problem with strategy A. If you recruit high performing people, they were higher performing in a different organisation.
Yes, agreed. All right. There's a whole lot of assumptions here which are unjustified. It also assumes that you can get the effect instantly in strategy A, but I have modelled that it takes you between 1 and 2 years to get the effect of strategy B in place. So, but just for the sake of argument, bear with it. The return on investment in Company Alpha is pretty good. It costs you 0.5% on gross margin to implement that strategy, and the return, because you've moved up that performance scale, gives you 2% back. So your ROI is ×4. Strategy B is likewise after 2 years, and by 5 years it's really pretty big. For Company Omega, strategy A, the ROI is not that great because you're spending a lot of your money on systems engineering, and because of your business model and your the movement between margins in your top, middle and low projects, you're not getting that greater return. And because of some of the reasons that Richard's described, that's a really high risk strategy. So actually, your only option, other than changing your business model, is to do to grow your own and take a while doing it. It's a long-term strategy, but it can work, which is good news, because when I put this model together in the first place, I wasn't sure that where any strategy would work for Company Omega, but it appears to. Okay. Right, that's enough on that one. I'm going to spend a very short amount of time looking at Eric Honor's research. That's Eric, and how to get hold of him. His research question was, again, how much systems engineering is enough? He had different categorization of activities, not the same 11 that the NDIA study did, but what he did do in his research, which he wrote up as a PhD thesis and sailed through, is that he mapped the categorizations that he used to 5 different standards, and it worked fine. He did 90 projects. It was over 100 for the NDIA study. They were not anonymized, but they let him really look at the data and challenge the objectiveness of the effectiveness assessments. Half of them were US DoD. The rest was split between non-US defence. UK, okay, right. But Australia, definitely, and I think BAE Systems UK. Some commercial systems development and some space systems. And he did his own curve fitting for overall systems engineering and by activity, and did some analysis of variance by postulating what would happen if you moved effort from one activity to another, or from non-systems activities to systems activities. Here are his major results. Strongly quantified relationship between systems engineering effectiveness and program success, and he claims an even higher correlation than the NDIA study, and an optimum activity level is 14.4%, and that's over the whole life cycle. Sorry, over the whole life cycle up to the point of delivery. No correlation between systems engineering activities and technical quality. That's an interesting one. Why not?
The contractors don't get paid for technical quality, they get paid for meeting the requirements.
Yes, that's right. It's due to the nature of the contracting relationships. The project is deemed not to be finished until the requirements have been met. All right, satisfactorily. So there's a completion criteria which does include technical quality. So the end technical quality at the point of delivery has been normalised. Now, I think, Bruce, that that's not true in the rail industry for reasons which we have discussed separately. That the requirement is finished at the point of delivery, whether it's met all the original requirements or not. So if you repeated this study in the rail industry, you might get significantly different results. And he's developed a methodology for estimating the optimum effort in each of the activities against the project based on some program characteristics, parameterization? Yeah, okay. I'm not going to go there, but read his PhD thesis. And that's his curve for actual divided by planned schedule versus equivalent SC effort, which he has renormalized for competence in a way that I don't fully understand. But again, you've got a crossover point somewhere between 11 and 14, 15%. And he's got two different studies repeated at different timescales, which is also interesting, and good correlation between the two, which is also reassuring. You could draw any number of regression curves through there, and I still stand by my assertion that you start to reach the law of diminishing returns around 8%. But Eric's analysis shows that you still get increased return on investment by reallocating effort to systems engineering activities right up to 14%. Similar for cost, very similar in fact. Okay, and that's how he deduced the 14% point. He looked at his actual over planned cost against equivalent SE effort, did the analysis of what if you moved effort from elsewhere into systems engineering, and that's the dotted red line is his return on investment, and he looks at where the points cross. But if you put error bars on that, then you might start to say, well, I'm getting a bit nervous about allocating more, somewhere between the 8 and 10% mark. So, feedback, comments on that. What's happening towards the right-hand side of that blue line?
It's making things worse.
Yes.
It's actually making things worse.
You're doing more or more effective, you're more probably, systems engineering, and your business performance in terms of cost and schedule is getting worse.
Sort of example of the need to tailor the process, you don't just keep going.
Yeah.
I have heard requirements discussions about should a dimension have its tolerance be recorded as separate requirements because they have separate traceability and rationale.
Yeah.
Perhaps out there going, you're putting dimensions
Yeah.
on drawings into doors, you must be lunatics.
Yes.
Yeah.
Well, okay. Eric's summary of the behaviour to the right-hand side of that inflection point is you are now reaching paralysis by analysis. Yeah. You're over-egging the pudding. I always describe the skill set of a really good chief systems engineer is to know which bits of the process he can safely leave out. And I stress the word safely. Okay, so he's got some spot points here. But at that point where you are only spending 1% of your budget on systems engineering activities, not only is your overrun 53%, but your return on investment in spending more is 7-1. And actually, Kuldeep Garatia gave a keynote on behalf of London Underground at the Incosi ASEC last November, and he pretty much came up with exactly that figure for moving down that blue line in terms of allocation of systems effort within London Underground, or Transport for London, to be strictly accurate. Yep. Okay. need to skip ahead. So you can look at this slide later. It's got a breakout by system engineering activities. So those are his 8 activities that he put within his study, and he looked at the optimum breakdown of those activities over the best performing programs. And he's looked at characteristic shapes, again, sort of top third, bottom third, or I don't actually know what fractions he used, but what does the shape of those activities look like for successful and poor programs? Poor programs are characterized by more systems integration and more verification and validation because it keeps failing testing. You keep reworking it and having to do it again. And how to get it right is to spend more on mission and purpose definition, which is an interesting sideline from requirements.
So that's the stuff you do before the contract.
Yes. Well,
Yeah.
or you can be funded to do it on contract, but yes. And more, technical leadership and management. And he said, because he played tunes to get those return on investment curves by reallocating effort from one activity to another, he says, if you optimize your program for technical leadership and management, everything else falls into place. All that says to me is that you've got good engineering governance on a project. So it's not rocket science, even though rocket science was some of the programs that he looked at. Okay? Comments on Eric's research?
Emphasis on good.
Yeah. There's still bias in the data. Both studies, so towards the good end of business outcomes. Yeah. And he did challenge some of the too good assertions by some of the responding organisations. No transportation projects. That's one of the reasons why I'm not speaking on behalf of Network Rail, because neither study have any transportation projects or no significant numbers of transportation projects in the survey responses. The survey responses were from a principal contractor point of view, the engineering organisation charged with design and delivery of the project. It does not cover contracting or client side acquisition organisations. So Network Rail is primarily one of those. The MOD is also one of those. So right-sizing the systems engineering effort in the organisation, this model does not apply to us. Okay, the actual answer about the size of systems engineering is likely to be much smaller. And what we don't have is a model from the full extent of the supply chain.
You started with the Jack Green's value cycle.
Yep.
Totally different research than you did. So people put the organisations where their responses were, or where they were on the value cycle, and then that explained why they had different views of the world. You could look at where on the value cycle have the companies responded, where they work.
I think they would all consider themselves to be, yes. There is some correlation depending on how much of the purpose, being involved in the solution, in the intervention strategy and the validation strategy in the revised operating environment. Yes, there would be a correlation with that, but it's not the ongoing operations and it's not the client side. Yep. Relative to Philip's model, value assessed at the point of delivery. Sorry, I'm moving too close to the speaker. Paralysis, I covered that. Okay, so correlation between the two studies, I looked at what both were telling me. If you're spending less than 2% of your development effort on systems engineering or integrated engineering activities, then the ROI of improving or augmenting your systems engineering is probably 7 to 1 or better. Yeah. Your optimum does not, it starts to flatten out at 8 to 10%. Eric recommends 14%. When I played tunes on my company Alpha, company Omega model, it can still pay dividends depending on your strategy at 20%. Management and of engineering activities was what makes the biggest difference from Joe Alm, and technical leadership and management, Eric Honor. They're very similar. And the next biggest is requirements, and within that, mission definition from Eric's study. Different measures of statistical significance, but the positive correlation of systems engineering with business effort in both cases. Okay, so that's a good outcome for us. Right, I'm overrunning wildly, but organisational evolution, I'm just going to say this is how a company typically evolves. You've got a project manager and he's got various suites of engineering reporting to him in disparate disciplines and a quality assurance function. And he goes through a typical V life cycle like this. And what happens is you run through that with your 4 engineering disciplines running separately, and when you try and integrate them, you get chaos. Okay? Yeah. Well, no, keep going. No. The first thing most companies do is appoint an integration engineer. Okay? What happened there? Yes. So once they've added an integration engineer, his responsibility is to take the problems that occur in integration, sentence them, and put them back for rework, back into the development life cycle. The next evolution is that you think, well, that's actually not enough. We're going to call him a systems engineer. We're still going to get him to do that sentencing, but we're going to try and elevate it so that we do root cause analysis of those design problems and improve the quality of the requirements. You still get rework, but hopefully, if those lessons learned on design to requirements are learnt, you'll get less rework the next time. Then after a couple of further iterations, you get at a position where mature organisations have systems engineering, might be called engineering management or product development management, are put in charge of gluing the other disciplines together, and hopefully you get less rework. All right? And the studies tend to show that. Sarah Sheard wrote a great paper nearly 20 years ago now on 12 different types of systems engineering role, and she enumerated them like that. My argument is that those roles don't appear at the same time. You get the glue among the subsystems and the validation and verification engineer first, and then you go to systems analyst to do the sentencing, requirements owner, and so on. And you only do the technical management quite late on in that organisational evolution. And that means there's a definite time order in which those roles appear, because that's the rate at which the organisation is ready to accept them. You get glue and IVVT engineers first, because that's where you first observe the problems of not doing it. Okay? And so on. It has to happen in that order, otherwise you're trying to push the organisation faster than it will go. And Mike's got extensive experience of that. Okay, so finally, how good is your organisation at supporting systems engineering? How good are your systems engineers? How are you going to quantify that? Well, individual systems engineering competence, used properly, very good at assessing the individual, but not good at assessing teams. Yep. CMMI, I'm not sure it tells you what you want to know. An organisation with several diverse business models, in theory, CMMI level 3 and above can only be reached by organisations with a homogeneous house style. So it's not going to correlate very well with the results of this study. So there's again something missing there. One last warning, correlation is not the same as cause and effect. Okay? Just because the activities correlate with business success, that doesn't mean that fixing them will necessarily cause business success. And this is the required response to journalists who confuse cause and effect with correlation, or business managers. And the second one is about the Liars Club, which is a systems dynamics artifact, which is that everybody furiously pretends